everybody. Welcome to our webinar today on using software engineering to help reduce medical errors. As we start, we're going to go through a few logistics. As many of you are starting to join us, you've got the option to join via your computer, your cell phone, or tablet using the WebEx app. Whichever way you do it is up to you. If you're having any technical difficulties, please submit your questions to us through the Q&A box, and we'll do our best to help you with that. In fact, at any time, you'll have the opportunity to submit your questions related to both our speaker's topic as well as the mentoring-related topics. Your questions will be answered by either our speaker during our live Q&A session or throughout the session as a private response. As you can see on your screen on the bottom right, this is the Q&A section, where you can submit your questions and the speaker will be able to view them. Throughout the presentation, we will be having some polls for you to answer. Please don't try and click the actual large screen. On the right-hand side of your overall screen, you'll see a polling section. I will let you know when the polls are open to be answered, and you'll be able to see the overall poll results after each poll closes. Let's actually try out a poll. The polls are now open. We want to know if you plan to study software engineering or are planning on being a software engineer. Select one answer, but remember, don't click the PowerPoint slide. Make your selection in the poll area on the bottom right. Your available options are, yes, I'm planning on studying software engineering. Yes, I'm planning on being a software engineer, both or neither. If you're having any trouble selecting or using the poll tool, please submit a response to the Q&A section and one of our staff members will assist you. As you're answering that, if you haven't heard of our CRA-W programs, it's an academic long research opportunity for undergraduate students. Applications open soon on April the 18th, so you can start working on your proposal today. You can find more information on our website, CRA-W.org. The polls have now ended, and we can see that many of you are planning on being a software engineer after studying software engineering. So you can see that we have a lot of people that are interested in our topic of today. At the end of our webinar, we will actually be announcing a lucky winner of a CRA-W polo shirt, so please stick around to see if it is you. So as the host of this town hall, let me introduce myself. I'm calling in today from the University of British Columbia, where I'm a professor in computer science and the Associate Dean for Research and Grad Studies. My current research focuses on software engineering as well, like Lori, with a particular interest in improving the productivity of knowledge workers. I'm also a CRA-W board member co-organizing these town hall events. It's my utmost pleasure to be introducing Lori Clarke. Lori is an Emerita professor in the College of Information and Computer Sciences at the University of Massachusetts Amherst. Dr. Clarke's research is in the area of software engineering. She's on the initial developers of the first model checking systems applicable to software systems. And these days, Dr. Clarke is focused on applying software engineering technologies to detect errors and vulnerabilities in human-intensive processes, such as healthcare and digital government. Let me turn it over to Lori.
Thank you, Gail, and thank you everybody who signed on. Unfortunately, we don't have video, but I hope you can all see the slides and we'll be able to ask questions. So let me start out by talking about how did I get involved in this particular area, because I didn't start there. As an undergraduate, I got my BA in mathematics at the University of Rochester, and after I graduated, I did work as a programmer at the medical school. But at that time, I had really had one class in Fortran programming, and I found it really frustrating because there were a lot of interesting problems and I just felt like I didn't know enough about how to solve them. So I decided to go to graduate school. When I applied to graduate school, I thought I was just going to get my master's and then go on. But I got very interested in research and then changed my plans and went on for a PhD. After I graduated, I went to University of Massachusetts, Amherst, and I've been there ever since. I've taken some sabbaticals, I've been visitors, but basically I have been at UMass throughout my career. So in terms of my research focus, as Gail said, I've really focused on software engineering. And software engineering is really concerned with how we can develop more reliable and better software systems. So I've been really concerned with the reliability part, and I've been working on approaches for helping with testing, how we can automate testing, and reasoning techniques, how we can prove and verify things about software. And to do that, you need to have an understanding of what it is you're trying to prove. So that got me interested in how you represent requirements. And then in developing all these tools, I became very interested in better support within the development process, so object management and how we do things like software architecture. So software engineering, and both Gail and I are in software engineering, it's really a wonderful area for doing research. There's always interesting problems, and systems are always getting more complicated. Used to work on sequential systems, now there's distributed systems, internet-based, cloud-based, database, so on and so forth. So it's a really expanding area with lots of interesting issues to pursue. And as software has become just a really integral and important part of our infrastructure, concern for safety and security have really increased. So it's been a terrific research area, and but I've sort of swayed from that. And how did that happen? One day, so Gail, can you get the slide where the photos come up?
Yes, I do.
Okay, so really, this is, I just wanted an excuse for putting up pictures of my kids and my family. So these are my two sons, daughter, and husband at graduation ceremonies, because the story I'm going to tell you about happened at graduation. So my husband and colleague, Lee Osterweil, was the dean of our College of Natural Science and Mathematics. And during graduation, he had to sit up on the podium, and he was sitting next to the dean of nursing. And she said to him, you know, nursing is becoming so dependent on technology, there must be some interesting research projects that people in our two colleges could pursue. So they talked a little bit about the kind of work we did in software engineering, the kinds of things that were happening in nursing. And so based on that, she introduced us to the person that's shown in the next slide, Nurse Beth Henneman. And Beth's work is on medical safety. And so she told us about the problem with medical errors and how there basically is a crisis in healthcare. So the question that we formulated was, could techniques developed for analyzing software systems be effectively applied to medical procedures to help reduce errors and improve outcomes? So this brings up our next poll, and that is, how many people do you think die in the U.S. a year from avoidable medical errors? And the answers are less than 100, 250,000, 4,400,000, or more than that.
Get your answers in so that we can represent you.
So let me just give you a little background while you're thinking or trying to guess what the answer is. There was a Institute of Medicine report that was published in 1999 that was called "To Err is Human." And that basically was one of the first studies that looked at medical errors. And that really is what got the ball rolling in terms of recognizing that this is a really important area.
So, Lori, we have the poll results in. We have 40% of our respondents think that it's $250,000 a year. 33% believe it's $440,000 a year. 20% more than $440,000 a year, and 7% at less than $100,000 a year. So maybe you can tell us what the right answer is.
Okay, so the right answer is 440,000. So, which is really a huge number. So that first study, the 1999 study that I was just mentioning, they estimated that it was just under 100,000. But as they've continued to study it, it's become clear that it's much larger than that. So the next slide, basically to put this in context, this isn't one where there's a poll, but just think about what are the leading causes of death in the U.S. and what would you put as the top leading causes of death? And if you click on that slide, Gail, it'll come up with the top 4, where heart disease is 611K, cancer is 584K, and medical errors at about 440K. Makes it the 3rd leading cause of death. And to put that in context, go to the next slide, and it shows this plane, and basically click again and click again, and you'll see that there's showing 3 747s. These were filled with people, and they crashed every single day. That'd be 3 plane loads full of people dying every single day. That's how you'd come up with the 440,000 deaths per year. So it's really an incredible number. And so when I say it is a crisis, that's not an exaggeration. So you might wonder, why is that? Are people just so callous? There was the next slide talks about 2009 National Research Council report. And this report looked at the problem, and they said that this problem does not reflect incompetence on the part of healthcare professionals. Basically, it's a consequence of the inherent intellectual complexity of healthcare taken as a whole. If you look at the pictures on this slide, it's showing some medical procedures, and you can see that there's a tremendous number of devices, teams of people. So it's not like a doctor talking to a patient and doing something wrong. I mean, that does happen. But very often, you're talking about teams of people who have to interact in a very critical and complex way. And then this 2009 report goes on to say that the medical care environment has not been adequately structured to help clinicians avoid mistakes or to systematically improve their decision-making and practice. So a question for us is, what can we do to help improve the environment to help avoid mistakes? And that's what I'm trying to do in my research. So the next slide talks about medical procedures are really, or can be viewed as complex distributed systems, so to tie it back to computer science. So in fact, we would say that it's not just any distributed system. They tend to be what we call human-intensive systems because people play a very important role. So there's software, there's hardware, but there's human performers. And the humans are not like end user. They're really central decision makers. They're right involved in the procedure, in the process itself. Now, that humans have a lot of ingenuity, and that can be really good. But humans may get distracted, they might be exhausted, and they just might make mistakes. And so when we look at these procedures, we have to consider humans and how they can affect the outcome. Of course, you could have errors in the hardware, you could have errors in the software, but really humans are probably one of the more error-prone components in this process. So Gail, if you click, it'll bring up a figure of really a control flow graph figure of what this a human performer might look like. So we're saying this is the this might be a control flow graph for one of the performers, and this is maybe it's a nurse, and the nurse has to repeat something every 15 minutes or whatever. And if you click again, there could be another medical professional, and they have the tasks that they have to do and various decisions. And you click again, and there's a third control flow graph. And this sort of is talking about 3 people in a team having to do very different things. And if you click again, red arrows come up, and that's really to just show the fact that there could be synchronization that's going on. So we have parallel processors, it's one of these control flow graphs, and we have synchronization and communication that has to go on. And everything we know about distributed systems, we know that it's really hard to get them right, because there's so many different ways that these systems could execute in parallel. People can't wrap their head around all of them, and errors can happen. So if we go to the next slide, that shows an overview of the approach that we've been using to this problem. So we first try to model the medical procedure that tends to be error-prone. Then we use different techniques to evaluate it. So the 3 that we look for, and I'm going to show you just quick examples: sequence errors, safety vulnerabilities, and inefficiencies are 3 of the prime techniques we use. If we find errors, we can't tell the medical professionals how they should change their procedures. We have to show them the problem they have to meet, and they have to decide what they need to do to make it a better process. And then we can model it, and we can see if those errors persist, new errors were introduced, or if it looks like an improved process. So I'm going to take that model of what we're doing, next slide, shrink it down, and look at the model. So we're a little short on time because I had technology problems to get started. So I'm going to just very quickly go over what the modeling language looks like. So Gail, if you click, it brings up a description of the process. And this is written in what's called Little Jill, and it's a graphical view. And the very high-level step there, single unit transfusion process, is shown. And then underneath it, there's sub-steps. Those would be the tasks that make up that high-level process. And that consists of bedside checks and prepare for infusion and so on and so forth. And then each one of those can be decomposed and so on and so forth. So this doesn't really fit very nicely on the screen because you'd like everything at the same level to go across at in the same horizontal. But you can see how you can just continue to decompose a task. And the arrows that are going, like with the single unit transfusion process, there's an arrow in that box that goes from left to right. That means those sub-steps are performed sequentially. And if you look at the step that says post-transfusion work, that has an equal sign, which means the sub-steps underneath it are done in parallel. And with this notation, we can have recursion. There can be predicates on the edges. So you can basically support all the control flow that you need. There's also exceptional behavior, because it turns out in medical procedures, exceptions arise all the time. And here, if you look under access patient, there's a yellow sticky that says an exception, adverse reaction. Well, we'd look up the tree, and find the handler for that exception. So it's very much like what you would have in a programming language where you have exception handling. But it provides a nice way to describe the handlers. And so if you look at the very top step, there's a red X, and off of that is descriptions of handlers, and then they can be also described in a lot of detail. So this is just so you can see it's a task decomposition. And when it's laid out nicely, the medical professionals can actually look at it and review it and say, oh, this isn't quite right, and I think we need to do that. This should be done in parallel. We go on to the next slide. It shows a textual, basically a hyperlinked textual view of the same process, where it shows the different steps, and if you click on one of the steps, you would go to its description and so forth and so on, so that if they prefer, they can see it as an English description. So that's basically our modeling approach. I should say that it takes quite a bit of time to model the procedures carefully, and we use a number of techniques to validate that the model matches the actual procedure. So we might use eye tracking, for example, or we might shadow the actual performers. Let me just talk about the evaluation, again, at a very high level. So if you go on to the slide where I'm showing the control flow graphs with the red arrows, now this would be a very, very simple process description, but we might want to know, well, can event A ever happen before event B? And that's the kind of questions we can ask, and then we can apply techniques. There's one called model checking, which would develop which could sort of enumerate all the possibilities that you might be able to execute the process that's described by these control flow graphs and determine if that could happen or not. Now that gets very, very large, so there's optimization techniques, but you can answer those kinds of questions. So you should click again, Gail. So we use model checking techniques to verify, basically mean to prove if a stated property holds or not, meaning all possible ways of executing it, or if it doesn't hold, we can provide counterexample traces that we can then show to the clinicians and say, here's where there's problems. So if you click again, I have an example of a very simple property that's just making sure that you check the ID band before you infuse a unit of blood. And I think because of time, I won't go into this except to say that you really have to get all the details of a property right. So, for example, for those of you who understand finite state automaton, you can see that we start in state 1. We can go to state 2 if there's an ID band that's present. But we can also check for the ID band more than once. There's no harm in checking repeatedly, but before you transfuse a unit of blood, you have to check. And this also says before each unit of blood, you have to check. So that's the kind of level of detail that you have to get, and then we would automatically determine if the process model adheres to this property. So that's one analysis technique. Let me tell you about a vulnerability analysis that we do. And so that's on the next slide. And here we use a technique that's from industrial engineering, and it's fault tree analysis. And this is just a schema to give you a sense of what a fault tree looks like. And the very top box is the hazard. That's the thing that you don't want to happen. And then you basically would say, well, how could that hazard happen? And you use gates, or gates, or and gates. So the gate that's under that first box that says hazard is an or gate, and it says, well, that hazard could happen if one of those two things that are hanging off that gate could happen. And then the one on the rectangle on the right-hand side, it has a and gate, and it says, well, that event could happen if the two rectangles underneath of it, if both of them, the conjunction can happen. But going on to the to the next slide, we can take that process model, the same process model that we used to do the model checking, but now we're going to do fault tree analysis, and we're going to propose a hazard. And I know you can't read this, and you don't need to, but our hazard is that the wrong unit of blood is given to a patient, and you say, well, how could that happen? And we use the process model to create this fault tree. Now, this is a tiny little process, and so this is a really small fault tree, and usually they have thousands of nodes in them, so they're quite complex. But one of the interesting things you can do with fault trees is you can represent them as a Boolean expression, and you can say for a particular event, I can't point, I can't show you, for a particular event, how does that happen, and you can represent it in terms of the events that are attached to it with an OR gate. And then you simplify all that, and you come up with an expression, and you put it in disjunctive normal form. And that means for each disjunct, if the terms in that disjunct are true, then the hazard's going to occur. So those disjuncts all provide a description of what would cause the fault to occur. For example, if you have a term in this disjunction that only has one event in it, that means that if that event occurs, usually the event is that it was done wrong, then that causes the hazard, and that would be a single point of failure. And usually when you are concerned about safety, you wouldn't want to have a single point of failure. And you would look at these clusters of events that could cause the hazard, and you might know something about their probabilities. You might look at things and say, well, gee, that's a very difficult task, and it's being done by the same person, and that could cause the hazard. And so you, based on that information, you would want to change the process model and subsequently the process so that it was more resistant to those kinds of problems. So let me just, I hope that gives you a sense of how it works. The next slide talks about how we can also worry about inefficiencies, and we can use the process model to drive discrete event simulations. And we can provide information about how long do those tasks actually take, and we can show a distribution of patients and situations, and we can get a sense for what the time bounds are going to be. And what's being shown in this figure for the discrete event simulation is what happens if you change the number of nurses to patients. And if it's a 1-to-3 ratio, then the time is much less than if it's 1-to-5. And so you can experiment with changing the process and see how that impacts the patients and the patient flow and the doctors and so on and so forth. So let's skip on to the next slide, which is sort of summarize some of the results from this kind of work. And first, sort of truth in advertising, mostly we found errors in our models and in our description of the properties. And this is like when you write a program and you start to execute it, you usually find lots of errors because you made silly mistakes. And that's the same thing here, especially when you're dealing with concurrency and exceptions. It's easy to make mistakes. But after you get rid of those problems, then we really started to find really important errors that really related to errors in the process. So using the fault tree analysis, we found single points of failure that the medical professionals were not aware of. We even found deadlocks, which was sort of surprising. And that is where, for example, a nurse might be waiting for something from the blood bank, and the blood bank is waiting for something for the nurse. If you have ever been in an emergency room, you wouldn't be surprised if this happens. And eventually, somebody says, well, this is taking way too long, and picks up the phone and breaks the deadlock. We found examples of, with the chemotherapy, where it was possible that they would be using stale data, which is, since they're using a very powerful drug, it's really important that the data on the patient be very up to date, and so on and so forth. We've done a number of case studies, blood transfusion, emergency room flow, cardiac surgery, and the chemotherapy. With the chemotherapy, we were lucky that they had been keeping a database of errors that reached the patient. And there was really only a small number of errors that would reach the patient every year. But after we worked with them on their processes, they saw a huge reduction in that number, which is really, really great results. So I just want to go on to that. So this work, we've been analyzing the processes. It's called static analysis because we're doing it sort of offline. But our recent work is looking at how we can use these processes to actually drive and provide guidance in a clinical setting. So this picture shows the process model all the way on the left, but all the way on the right, there are some medical professionals, and what they're looking at is what we call smart checklists. And these provide them guidance based on all this knowledge we have about the process, and so we can show them what needs to be done next. There's been some studies done that show that checklists are useful in a medical setting, but medical professionals tend not to like to use them because they're so simplistic. And we're hoping that by providing a much richer view that really gets updated depending on the patient and what's actually happening, that we can provide checklists that they'll find more useful. So there's a lot that goes on between we have to be able to keep track of these events that are happening in the real world so that we know where we are in the process, so we know what to show, so that there's an event interaction manager. And when there's a deviation, we have to be able to detect it, and we want to be able to provide some kind of explanation. So there's a lot of interesting problems involved in this. And the next couple of slides really just show an example of walking through what the SMART checklist might look like. So, Gail, if you bring up the SMART checklist for this poor patient, Margaret Gary, and there's a green check button, and this would be showing this blood transfusion process, and if you click that green button, then you see more of the process. And this is showing some possibilities, some things that could be done in parallel. And if you click the button for obtain vital signs, it brings up some more, and so on and so forth. So this is to give you a sense of what it might look like. And this could be on a display in the hospital room where everyone could look up and see where they are in a particular process and who's doing what. And Gail, if you skip over until there's basically a table, administer a single unit of blood product. This is, in addition to providing that SMART checklist, we can provide a summary of actually what happened in the procedure. And this is just an example of what would be automatically generated after we have provided this guidance through a process. And right now, medical professionals have to create a summary usually after the fact, and it takes a lot of time, and they hate doing it. So we're hoping by creating it automatically, letting them edit it and improve on it, will save them time, and they'll find it to be appealing. We're also hoping it'll end up, by using this technology, it will end up by reducing errors. So that brings us to the next poll question, and we plan to do some human simulations. We won't have real patients. We'll have mannequins that basically have vital signs, and nurses and nursing students will be doing blood transfusions on the mannequins, and we can see how well this technology works. But we wonder where we're going to find our problems. So this is basically a poll saying, where do you think we're going to have problems? Is it going to be just resistance to having automated guidance? Is there going to be too much divergence between the process and the model? And they'll get frustrated and say they won't use it. There were a couple places where they had to click when I showed you that example. Will there be resistance to entering additional information? Maybe all of the above, or you have no idea. Well, of course, none of us have any idea. We're really going to have to conduct this study to find out. But why don't you, I'm really interested in knowing what your best guess is about where we're going to find problems.
Looks like most people think it's all of the above, Lori.
That's a lack of confidence, huh? Anyway, I think it will really be interesting. We have had focus groups look at this, and again, these are medical professionals, and most of them have been very enthusiastic about having something like this. So, so I'm sure we're going to have some resistance. So let me just have one more slide, and that is, this is really a team effort on our part too, and I just wanted to point out that I have a number of collaborators. George Brunin and Lee Osterweil are two people that have really been most involved in this project from the beginning. And but we also, the people on the next line there are nurses, industrial engineers, doctors that we work with very closely. The picture with the X-ray machine is a number of medical folks that we work with, and a number of students have made major contributions to this. And the students could have gone on and on with the students who have made contributions, but these have been the primary contributors, and I just wanted to acknowledge them.
Well, thank you, Lori, for presenting your research. It's really fascinating. We're going to have the audience put in some more questions, but we've already had a number, and I think in the interest of time, we're going to limit it to one. So here's the question for you. What are the major medical areas that need coding or modeling to reduce medical errors?
Oh, there are so many. So the ones that we picked, the blood fusion, the chemotherapy, room flow, and the cardiac surgery are all ones where there are a number of errors. So that's why we picked those. In fact, we didn't pick those. People came to us and explained the problem. They're all very different, so from our perspective, we learn a lot from them. The emergency room has a large number of people who have to coordinate and interact. The cardiac surgery has teams of individuals, and there's like 3 or 4 teams that are working together very, very closely. So those areas are all examples where there's lots of errors. I have to say, unfortunately, in terms of most areas in medicine, you're not going to get that huge number that I told you about in the beginning if they weren't really pervasive in most procedures. So I hope none of you have to deal with the medical professionals soon, and if you do, please be vigilant.
Great. Well, I really encourage our audience to continue to ask questions in the Q&A box, and we'll make sure that those questions get answered offline. But right now, we're going to move on to the second part. We have about 15 minutes left for a mentoring session about mentors. So the topic today is mentors, why do we need them, and how do we find them? So Lori, I wonder if you can tell us a little bit about what a mentor is to you.
Well, just start out in general talking about a mentor. And this slide talks about how Homer said it was a wise and trusted counselor. And I think that most people would agree with that. And if you click, it will talk about a mentor is basically someone who provides you guidance and this counseling in terms of your professional, but also in terms of your personal life and how you bring the two together to succeed. And if you click again, Gail, it talks about a mentor as someone who takes a special interest in helping another person develop into a successful professional. So, it's just someone who is really going to give you honest and useful advice to help you really move your career and your life ahead. So I think if you look at the next slide, it's a poll, so we can get some sense of if the audience has mentors or not. So it asks to describe your current mentoring situation. If you have no mentors, if you've actively looked for mentors, if you have a good mentor, or maybe you have several mentors.
So maybe while our audience is answering the poll, you could tell us something about one of your best mentoring experiences.
So I have to say, when I was thinking about mentors, in high school, my physics teacher was a terrific mentor and very, very encouraging, since there certainly at that time were hardly any females in physics, and he was always very supportive. I have to say, when I was an undergraduate, I didn't really have someone that I would have considered a mentor. But in graduate school, and one of the wonderful things about graduate school is I think that most people find a mentor or two in graduate school that makes a huge difference in their life. So what about you, Gail?
I think I've been lucky to have fantastic mentoring experiences in graduate school as well. It looks like for our audience, half of them, roughly 35%, don't have any mentors, but 41% have several mentors. So it looks like we have people on both sides of the equation in our audience today. Maybe you can tell us a little bit about the research on mentoring?
Yeah, so if you look at the next slide, and the reason this is important, and it's been recognized that it's important, that research shows that those who are mentored achieve greater career advancement and higher work satisfaction than those who aren't. So, of course, there's always exceptions. So if you don't have a mentor, it doesn't mean you can't succeed or that you won't find a mentor sometime in the future. But it does seem to really make a difference. And I think people who have a successful mentor-mentee relationship feel that they gain a whole lot from it. So the next question asks about how satisfied are you with your mentoring relationship? Very dissatisfied, somewhat disappointed, mostly satisfied, or very satisfied. So I guess for those that have a mentoring relationship, we'd like to know, how is that going for you?
So hopefully our poll will open up in a minute here. There it is. It's on the screen now for you to be able to answer. Why do you think it's important, Lori, for someone to be satisfied with their mentoring relationships?
Well, if you're getting advice and you want to have respect for the person that's giving you advice, and if you're going to try to follow the advice, it's important that that be a trusting relationship. So I think it's very important to find someone that you admire and that you think will provide you with good advice and will be an honest counselor.
We're just waiting to see our poll results come up. It's hard to know where they're going to end up, so it's always interesting to see the results actually show up. Here they are. We have 8% are very dissatisfied, 23% are somewhat disappointed, 23% are mostly satisfied, and 38% are very satisfied. So it's great to see that at least the highest percentage is in that last category.
Yeah.
Shall we move on to the next mentoring? Shall we move on to the next poll?
Yeah. And this is asking about what are your highest priority question about mentors. Why do you need them? What can mentors do for you? How do I find a mentor? And what is my role as a mentee? So if you sort of give us a sense of what's most important to you. And while you're doing that, let me just say that, if you are dissatisfied, continue to seek out people that you think will be good mentors. can be frustrating at times, but I think if you find someone or two, it can be very rewarding.
Definitely true. So we're just seeing if our polling results come up, and it turns out that nobody is in the first category of why do I need a mentor, so that's great. We have 7% wondering what can mentors do for me. We have 67% wondering about how to find a mentor, and 27% wondering what their role is as a mentee.
Okay, so maybe based on that, and because we're a little short on time, why don't we, the next slide is about why do I need mentors? And so I think people seem to understand that. And maybe the next slide, which is a poll, and talks about what do you want most from your mentor, really is answering some of the questions about what can you get from your mentor. So these things that are listed here, career advice, academic advising, self-confidence, advice in building a professional reputation, access to a professional network, support for recommendation letters, etc., and emotional support in tough times, I wonder how the audience, which ones are the most important for them?
And we'll see what the results come up with. Looks like they're coming up now. Oh, here we go. So 43% would like to gain career advice. That's by far the highest. And then it's somewhat equally split for all the other categories, Lori.
Okay. So I think that career advice is really important. You know, you start out wanting academic advising about what courses to take, and that's a simpler form of mentoring. If someone understands what are your requirements at your institution and knows something about who are the good teachers and what combinations of courses you want to avoid. But I think that career advice is really very, very important, and that's one of the major reasons for trying to find a good mentor when you're in school. And someone can talk to you about the pros and cons of graduate school, different kinds of industrial positions, how do you situate yourself so you can get the kinds of jobs that you want. All of those things are really very, very important. And later on in life, when you are moving out of school, getting a good professional reputation, building that network is really important. And
that is great advice. And I think in the interest of time, since we'll be able to post the slides later, I'd like to ask one or two questions that are coming up from our audience, if that's okay. So one of the questions is, what if my mentor is too busy this semester? Should I get a new one?
Well, you know, it's always good to have more than one mentor because basically it's your career, it's your life, and you have to make the decision. So it's not bad if you hear a couple of different points of view. And also, if one person is busy, and people, you know, sometimes are busy, and, you know, it's not because they don't want to help you, they just don't have time, then it gives you some options. So I think it's always better to have more than one mentor. I know some it might feel like, oh, you don't have any, and now I'm saying have more than one. But, you know, we're going toward the ideal, and it's not something that you have to do this next week. You know, in the course of your career, your education, you should be looking for mentors, and it's good to have more than one person that you can seek out for advice.
That sounds like really good advice to give people. Can you have mentors from multiple areas? Do they have to be from academia, or can they be from industry? Where should one really look for mentors?
So I think we even have a slide about that, but really you want to really keep your eyes out for mentors. Certainly it's people that are teaching your courses and you start to develop some kind of relationship, that's a real good source. But if you have a job, you have an internship, you might find that there's people there. Or it could be outside of your field. It could be someone who's in a different field that you've come across, either in your courses or in, you could meet them at various events and things. Someone who you value their advice. You can seek them out and see what they have to say. So, I think you should just be looking for people that might be able to provide you with wise guidance.
That's great. And one last question. Is it okay to just ask someone to be your mentor?
It is, but usually if you go to talk to them, you could just start asking them questions that a mentee might ask. You could just say, I really enjoy your comments in class, and I have a number of questions, not about class, but about my career planning. So you're not really saying, will you please be my mentor? But you're coming and asking advice. And if they turn out to provide you with good advice, then you should thank them. And then you can say, I really appreciate this. Would it be okay if I come back and talk to you, next week, next month, or whatever? So you start to develop that relationship.
Well, I'm really jealous of our audience because I wish I'd had that advice back when I was an undergraduate. Thanks so much for it, Lori. I think we're going to move to the end of our webinar today, and I wanted to start by really thanking Lori for her time and her interesting insights both into how we can improve medicine through the use of software engineering techniques. Seems really exciting, and also such great mentoring advice to have, and I hope everybody is able to take advantage of it. We do have a number of outstanding questions, and we will make sure that you get access to answers through various mechanisms. We'll reach out to you and make sure that you do get answers to those. So in terms of feedback, we're always trying to improve our webinars. We hope that you will take a little bit of time to answer a 1 to 2 minute survey. And you can see that there's a QR code on the screen that will take you to the survey. There will also be information provided to you in the chat window about how you can get to that survey. We'd like to announce that the winner of the CRA-W polo shirt is Jasmine Onfrey. I'm sure I'm not pronouncing your name correctly, but one of our CRA-W staff members will be reaching out to you in regards to your prize. And thank you for participating as well today. So with that, we do hope that you've enjoyed our virtual undergraduate town hall events. We really appreciate taking time out of your day or your evening to join us. Our next webinar will be this summer, and we encourage you to stay in the loop with our programs at CRA-W and upcoming events by joining our mailing list, which you can do by going to our website at cra-w.org. Another great way to stay involved with what's happening is to follow us on Twitter using CRA Women as the entry point to Twitter. Your feedback is really invaluable to us, so please do take the survey that will pop up after you close out of the webinar. We really are doing these for you, and we want to make sure that they're tailored to what you need to get out of them. So thank you to Lori, thank you to all of you, and really have a wonderful day or evening. We really do appreciate you coming to our webinar today.